Okay, so in today's revision session, we are going to see the contents of week 10 and 11. Sorry, 9 and 10.
Okay, sir.
So we will be covering some questions or just the theory.
We'll try to cover questions also. Uh, Theory would be very small. We'll try to cover some questions. So in week 9, we are going to see the contents are in week 9. Constraint, okay, optimization, then Lagrange is there, okay, and which is nothing but the constraint optimization, and the convex. In convex, we are going to see convex set and convex function. So this is in week 9, and week 10 is the KKT only, I think. Okay. So constraint optimization is we have given some function, okay, and we want to minimize or maximize, but it have given some constraint is there. So either could be any.
So to optimize a function, either to minimize or maximize, the process will be exactly same, or will there be a difference?
So here we are looking the cake. If we are so if we are doing with the KKT, so KKT have the minimization. We'll stick on the minimization. We are not going to in great detail, not even great in small detail, because there is very less thing have taught. And the here and the next is if it is not KKT, means more than one constraint is there, then we usually solve with the KKT. But if it is only one constraint is there, then we are look at, so either it could be minimizing and maximizing, because Lagrange's is for any kind of, if it is minimizing or maximizing, it's depend on how we are getting the critical point. So here, if it is already mentioned that minimizing or minimize the function and constraint is given, constraints are two types. We are generally see it either inequality, less than or equal to, greater or equal to, okay, either of this case, or maybe equality constraint. So we look at with the separately, okay. And if it is a mix, then the KKT comes. That is what the thing. KKT is the mixing or more than one constraint is there. It's a G1, this is C2. So either here it could be, if it is Lagrange's, we are dealing with only one constraint. So either it could be maximizing or minimizing. It's depend on how the question is asked. Okay. So If it is inequality constraint, so we are now the revising. So I will just write the.
So usually in KKT, we will have to take 4 conditions, no?
Yeah,
G1 equal to 0, G2 equal to 0, then G1 not
stationary,
equal.
complementary slackness, feasible and dual feasibility. Yes. Okay. So if it is inequality constraint, so we will find the gradient, okay? Gradient of the function, and find the gradient, and this gradient and gradient of g. Okay. So either you are giving it is a minus, so minus is there for the inequality, minus is there, but here the lambda is. If it is inequality, so we'll choose only the positive values of lambda. If it is inequality, for this inequality case, this is going to be minus lambda gradient of g. So in this case, we will take any value of lambda. So suppose I have a function, let fx y is equal to x square plus 2x plus y, okay, where the constraint is given g of xy is, let's say, uh, x plus y is less than, or let's say I can make it here equality or inequality. So let's say x is less than or equal to y square. So how we'll do this?
This is KKT.
Not KKT.
Okay,
Only one
single
constraint
condition.
is given. Yeah.
Only one constraint.
So all of you try this. Let me know where you are reaching it. Are you able to reach the correct answer? So find the critical points where you are getting the maxima or minima. Let me know. Find all possible critical points. All of it right.
So what are the constraints on x and y and lambda?
So constraints are this. This is a constraint.
The
This is the
value of
constraint.
dxy is not there, no? Or
So g
we
of
just
xy
have
is
to
going to be what? Is going to be,
x
if you think
minus
x
y
square,
square,
x minus
x
y square
minus y square is
less than
less
or
than
equal
or
to,
equal to 0.
this
And
is your g
x
of x.
less than y square is one of the constants for x and y, no?
Sorry.
x is less than y square is the constant on x and y. Like
On x
earlier,
and y. Yeah. Yes.
we usually have the values of x1 and x2 less than or greater than 0 or something like that.
Yes.
Instead of that, we have here x is less than y square.
Yes.
So if we find the value of lambda, we have to add all the values and the k is equal to 1.
Odd and sorry. So once you write the this equation, Lagrangian multiplier or Lagrangian equation, so after that, what you are finding? So
So value of lambda.
So what is the value of lambda you are getting?
So I got confused. We have to k is equal to 0 for finding value of lambda.
No. Why you are equating it? So let's do here. So others are who are trying. We can try. So of f we'll find, and then minus lambda time gradient of g. Gradient of f is going to be 2x plus 2y, and this is 2x plus 1.
Sir, here
So
lambda will
2x.
always be negative.
Positive, no?
No, means negative sign will be always there.
Yeah. Here it is negative sign will be there, no?
Always.
So we don't
Always.
have to find the Lagrangian.
Sorry?
We don't have to find the Lagrangian.
Find the Lagrangian means Lagrangian, this multiplier.
We'll have
This one. Okay, let me try it. So this is 2x plus 1.
Why are we giving a minus sign to this lambda? So in few examples we saw it's just the plus lambda of
So what is there in the lecture? It is written this one, or we can write this as a gradient of f plus.
Most of the graded assignments we saw it's just the plus sign.
Yeah. So this is the same thing, right? This is the same meaning.
But it
Either
says del f is equal to lambda of del g.
Sorry.
Del f is equal to lambda of del g. So without a negative sign on the right hand side.
Yes, sir.
Without.
So that is what is given as solutions in the graded assignments. Yeah.
Sorry. This here is minus, or what is that? Without sign of this one.
Yes, correct. Yeah.
So see here you have to be so that is why I intentionally gave. See here this is an inequality constraint. Okay.
Oh, yeah.
So either you are writing lambda minus lambda doesn't matter. Sorry. So it will matter here. It will matter here. If I'm suppose I'm writing like this, your constraint is your constraint is this one. So in this case, if you are writing Lagrangian equation, so here it doesn't matter. Either you are writing negative or
we need to include the minus signs.
Yes.
Got it.
So in the most of the equations, so in the graded assignment, I think this problem is not given. Inequality problem is not given. I think so.
Yes, sir. Correct.
Always the equality problem is given. In that case, either you are writing this one, okay, or gradient of f, all are actually same, okay. Or gradient of f minus gradient of lambda time gradient of g is equal to 0. Or you are writing positive one also.
Because we didn't have a scenario of having a negative lambda of del g.
So yeah, lambda could be anything in the case of equality constraint.
Got it. Yeah. So whenever we have an inequality, we should use the minus of lambda on the right hand side.
Yes.
So as default, we can always use negative sign because
at default you can always. So this one by default, always use this one or by this one?
Yes.
So if you do it here, so and gradient of g is going to be here. This is 1 and minus 2y. So 1 minus 2y. Okay. And now we have this equation. So 2x plus 2y is equal to minus lambda. 2x plus 1 is equal to minus 2 lambda y. This is what we have, right?
So the
Two
value
equation.
of
2 lambda है ना?
2.
Both sides are negative. It will be positive.
Yeah, this will be positive. So minus is going to be positive. Okay, I think correct. Now we have to find it here. So lambda value or using something. We have to find the x and y value. So see it here. This lambda is equal to minus 2x plus 2y. So 2x plus 1 is equal to 2. So 2 lambda is minus 2x minus 2y and then y. So still it is I don't know we'll reach to the answer or not. So this is 2x plus 1 is equal to minus 4x y and minus 4 y square. So we have 2x. So it is going to be tough now. Any other way to solve it?
so can we do by KKT conditions? I solve by that way.
So if we
Okay.
solve these two
I
equations,
got
also,
x is equal to minus 1 by 2, y is 1 by 2, and lambda is 0.
So KKT is nothing but the Lagrange. So how you are solving it?
Also, there are 4 conditions, right? First is
Yes.
stationary. Second is complementary slackness. Third
This
one
is the first. So this is the first one, right?
yes, sir.
This is the first stationary. The second is
Complementary slackness.
what is that complementary slackness?
A lambda into g of x is
Lambda into g of x.
is
Yes.
equal to 0,
Okay.
and primal feasibility condition is g of x y is equal to less than or is equal to 0.
Yeah, less than or equal to 0.
Fourth, fourth dual feasibility is lambda is greater than 0.
Lambda is greater than 0.
or is equal to.
Okay, so
That is
if we
equal
do
is equal to also there.
Greater or equal to. So we have this stationary, and now you are saying this lambda will use.
Yes.
So lambda time x minus y square is equal to 0. Correct?
Yes.
Okay, and these two are not going to help us much, right? So these two are, I don't think will help.
If we
Yeah.
write x minus y square less than or it is equal to 0,
Hmm.
and if we write then with from complementary slackness we check the interior. If interior point will satisfy, then we can check primal condition.
Okay. So this will give here lambda x minus y square is equal to 0. This will give x less than or equal to y square. This is already here. This we have. So now
it's the same set of equations, right?
this is the same set of equation you are getting. So now how you are solving?
So in complementary slackness, if we are assuming interior point is less than 0,
Okay, this is less than 0.
X minus y square, then lambda is 0. So,
okay, lambda is 0. Okay.
So we are putting in stationary condition. After putting values in stationary condition, we got values of x and y, and then check for primal feasibility condition. That was also satisfying. If
Okay. So this is case for when this x minus y is less than 0. You are not including equal to 0, right? Only
uh,
this less than.
yes, sir.
Yes. Okay. So in this case, if this is less than 0, we'll get lambda is equal to 0. Once we got lambda is equal to 0, so our these two functions we have, so sorry, these two equations we have. So from here, we got lambda is 0, so this is 2x plus 1 is equal to, this is lambda is 0, so this will be 0 here, so x is equal to, will get minus
half.
Minus
1
half.
by 2. And once we got here 0, so this is, we can substitute 2x plus 2y is equal to, this one will give 0, and this is minus half is there, so minus 1 plus 2y is equal to 0, so y will give half.
1 by 2.
So we have minus 1 by 2 and 1 by 2 point.
If we put in third condition, that was g of x y less less than or is equal to 0. That was
So it is
satisfying.
true, and it is true, both are actually satisfied.
Yes, sir.
So we got one optimum solution, minus 1 by 2 and 1 by 2. Okay. And you assume to be here less than, strictly less than 0. And the second case is when it is 0.
If less than was failing, we have to assume is equal to, we have to check for 4 condition.
X is equal to y square.
So if it is this case, then x is equal to, if this, so if
Y
this is
square.
done, then x is equal to y square. And x is equal to y square, then again we'll go to the stationary condition, these two equations. Okay. And then this is 2x plus 2y. X is equal to y square, no, we have. So, but lambda value we don't have till now, any lambda value. Okay. So
yes,
what we can do, this is 2x
so in place
plus
of x, we can put
y square. Okay, so this is 2y square plus y is equal to minus lambda. This will give, okay, and this will give. So please everyone observe it. We are just doing the calculation, because here either you have a KKT or Lagrange's multiplier. You anyhow you have to deal with the equation arrangement. You have to do anyhow. You have to find the values. So we are doing it here with the KKT or the both. Lagrange's is Lagrange's is also will follow. So, but if you are not able to do, then we are doing with the KKT only. So please try to see it, okay, so that we will not miss it. So this is 2y square plus 1 is equal to 2 lambda y. Okay, so now we'll use this lambda value to here, so that our equation will be single equation in one variable. So this is
It is
2y
2y
square
plus 2y, no?
2y.
Yeah,
2y
2y.
square plus 2y.
So this is 2y square plus 1, 2, and 2y square plus 2y, and then y. Oh, this is now cubic.
Negative sign.
Okay. Negative sign is there. Yes.
So it will y is equals to 1 by 2.
No, we will not use, no. Y is equal to 1 by 2 we will not going to use, because we are dealing with only now this case. We already deal with this one, strictly less than. And we got 1 point, minus 1 point, minus 1 by 2 and 1 by 2. Now we are dealing this case, equality case.
Sir, but this came from KKT. For like single equality, we should can we do it just with Lagrange multiplier, because that will be much easier, because switching between KKT and Lagrange will be little confusing.
Yeah, I will back to see started saying. So I will back to the Lagranges. Okay. I will back to the Lagranges. I am just doing with the KKT only this one. I will back to the Lagranges. So let me finish this one, then think it. But again, we'll try to solve with the Lagranges only because one constraint is there. KKT is for the more than one constraint. So
Yes.
this is 2y square plus 1. Yes.
Sir, sorry to disturb, but could you just
Yes.
show f of xy once? I just wanted to note it down and try it myself.
Yeah, this is.
F of x square plus 2xy plus y. Okay, sir. Thank you.
Yes. So this is, we have minus 4y cube and this is minus 4y square. And I will send to this side both. So this is going to be 4y cube plus 6y square plus 1 is equal to 0. And we have to solve this polynomial. And will this be a solvable? Just a second, let me see it once. There's the Desmos. Okay, so I'm doing it here for the time being. Okay, this is cube plus 6x square. Okay, plus 1. So root is here, very complicated root. Something 1 point. This is what it is, 1.5 if you assume it. So we'll get a real value. I mean to say we'll surely get a real value, because if we try to solve by hand, we'll not reach to the answer. That's why he uses the. So by this way, we'll get a real value, which is y is equal to minus 1.5. So if we have minus 1.5, then we can get easily. Okay, so once we have y value, then we can get x value also.
And
Yeah.
lambda value also.
Lambda value also. So okay, so if we have minus 1.5, then what is going to be the lambda value here? This is okay. So here, from here we'll get no. This is relation. Okay, yeah. Here we get it. From here this will get we'll get here. Yeah. From here we'll get lambda value. So lambda value is here. This will be positive, and this will be this will be negative. What is the final? Actually, why I'm checking? No, this here lambda should be positive. If we find after finally lambda, okay, negative,
here,
then we'll not use this one. Yes.
Sir, but here we are getting lambda is negative.
So now we are going to leave it now. No, so that is what
Yes.
I'm saying. That is what I'm checking the sign only. So here we are. So once we got this value, y value, okay, which is minus 1 point roughly, okay, approximately minus 1.5. So once we substitute it in this equation, we are getting this lambda is negative. I think it is going to be negative because yeah, because this side is negative and this side is going to be positive if you substitute. So finally lambda is going to be negative. So we are not going to use this point. So only one solution is this one by KKT. This one only. And now if you use Lagrangian here, so if you deal with the Lagrangian only, so if let's do with the Lagrangian only. So we have this is what we have, and here if you substitute this lambda value.
Sir, what was the function? X squared plus 2xy plus
Function is x square plus 2xy plus y, and g of xy is x square minus x minus y
X
square less
minus
than
y
or equal.
square.
So once we do the Lagrangians here, we got 2x plus 2y, comma 2x plus 1, 2x plus 1 equal to minus lambda time gradient of g, which is 1 and
minus
1 minus 2y. So now if you do it, 2x plus 2y is equal to minus lambda, and 2x plus 1 is equal to minus plus 2 lambda y. Now we have three variables. Here we have three variables, lambda, x and y, and we have to solve this anyhow by this way. And we only know one thing, lambda is greater or equal to 0. Not only greater or equal to, greater than 0. Lambda is going to be positive. So by this way it is going to be tough, is it?
Sir, so we can solve this. I'm getting y is equals to 1 by 2.
So yeah, so can you tell me how you are solving it?
Yes, sir.
Hmm.
So both this equation will just divide it like
By
so
2.
no, sir, no. So we can just solve it by like summing these two equations. We'll get 2y minus.
Okay, let's sum them. Yeah, correct. So this will be, yeah, if you subtract, no, summing means if you subtract, then yeah, correct. Minus and minus. So this will be out.
1. Yes.
2y minus 1. Yeah, correct. So now, yeah, thanks. We are
minus
at
lambda
some point.
minus 2 lambda y.
Correct. Yeah, in that is what we have to equation anyhow, whatever you are coming in your mind, just do that. Just be correct numerically and with the sign, negative or positive, and try to find it. So here, yeah, this is one way to reach it. So this is 2y minus 1, and this is a linear equation. So here is 2 minus y. So minus lambda will take out. So this is going to be 2y plus 1. Okay. So lambda is going to be 2y minus 1, or if you send it this side, 2y plus 1. Okay, you did this one.
Sir, I got the value of y.
So from here, what you are doing?
Sir, 2y, I took minus 2 lambda y to the left side. And then in the right side, it was minus lambda minus 1.
Sorry, this is correct, right?
Yes, this is correct.
So now you are
lambda is 2y minus 1 upon 1 minus 2y now.
Oh, okay. So I will back to. So I am taking here lambda as a common.
Sir, it is better
lambda.
To get y. To get the y in terms of lambda and put the value of y in the first equation.
Y in terms of lambda, okay.
And put the value of y in another equation to get the value of x in lambda.
Okay.
And put the value of lambda.
Let me.
Yeah, put the value of x and y in the third equation to get the value. It is
okay. So I am sending it this side. So 2y plus 2 lambda y is equal to minus lambda plus 1. And I am taking y as a common. So this is 2 plus 2 lambda minus lambda plus 1. So y is equal to minus lambda plus 1 upon 2 plus 2 lambda. And once we have y value, then lambda y value, then
it is 1 by 2, 1 minus lambda by 1 plus lambda.
Yeah, this is going to be okay. So this is we can write or rearrange 1 by 2 minus lambda plus 1.
1 minus lambda by 1 plus lambda.
Either you can 1 minus lambda and 1 plus.
Now it is in the form. Yeah.
Okay, this is the form we have now. Y value we have, so we can substitute in
first equation.
Substitute in first equation 2x plus 2y. So 2y is okay. So this is 1 by 2. So this is 1 minus lambda, and this is what it is, and this is minus lambda. So 2x is equal to, we'll send this side. If you send this side, 1 minus lambda. So means here 1 minus lambda, 1 plus lambda plus lambda. So or x is equal to 1 by 2 of all this 1 minus lambda 1 plus lambda.
Minus
So if
2x.
you find lambda value, then we'll get
minus 2x.
minus 2x.
So 1 minus lambda upon 1 plus lambda minus lambda, right?
Some
No.
minus na minus.
Minus
there
2x
is
is
1 minus
equal to
lambda
yeah.
upon
No,
1
no,
plus.
no, no, no. It will be plus only.
Yeah, it is
Whole
correct.
square is minus.
Yeah, it is now correct. So if you get the lambda value, then we will get x and y. So finally, if we substitute in the second equation here, it will be some equation of lambda.
So,
It is plus lambda.
sir, we
Here it is
are
plus.
taking 1
Yeah.
minus lambda
Sir,
plus
in the
1
second line,
plus
in the
lambda.
second line, sir.
Right hand
Outside
side,
bracket
so it's
will be
minus.
minus.
In the second line, it is minus 2x is equal
Sorry,
to
sorry. This is minus. So
Yeah.
minus and
Whole is minus.
whole is minus.
so
It
let's
is
do for yes.
It is lambda minus 1 minus lambda by 1 plus lambda. Not whole minus. Opposite.
Lambda minus 1, sir.
Yeah.
Either I can, if you are saying so, if you are rearranging, so this is lambda minus 1 and here is minus. So however, it's totally
Okay.
the arrangement. So let's do let's see how the lambda equation we are getting. So this is 2 and next is lambda minus 1, lambda plus 1 minus lambda plus 1, and this is 2 lambda, and already 1 by 2 will cancel out, so we can make it out here finally. Lambda time 1 minus lambda 1 upon lambda. This is what we have. So if we do 2 1 minus lambda, or let me write in this fashion. So minus I am making out. Okay. So minus 1 minus lambda 1 lambda plus 1. Okay. And this is minus 2 lambda plus 1, and this is lambda 1 minus lambda 1 on lambda. So I will send this side. So this will be 1 minus lambda 1 plus lambda will be common, and this will be 2 minus 2 minus lambda, and this will be minus 2 lambda plus 1 is equal to 0. Oh, there is no meaning of it doing this. So everywhere is lambda. So what is the lambda value? So if we got the lambda value, we are done. So
Sir,
if we solve this equation,
sir, can we put xy in constant
Lambda
equation?
lambda
Solve
square plus 2 lambda
In the
minus
third
1.
equation, put in the third equation. Because 3 equations are required.
no, only 2 equations we have. Third equation is what? Inequality constant.
Sir, which year's question is this?
Just curious,
No.
yeah. Do we get complex questions like this to solve?
No. I just
Okay.
this is I am just leaving now. Okay, this is
Yeah,
the
because, we
final
want
step.
more
Means
time.
yeah, I'm leaving now. We are on the session only. So I'm leaving now. So this is the final step. Means once we solve this, I'm leaving for you. Okay. So once we solve, and whatever the lambda value will get, only the real value. Okay. And lambda is going to be positive. So maybe if you are cubic, is this equation is cubic or is quadratic, whatever the things, means how many lambda value you are getting. If all are negative, then no, we'll not going to think it. If one of them or two of them is positive, then accordingly those are going to be the stationary point, and we'll get the optimum minima or maximum.
In a KKT question, if none of the constraints, not constraints, conditions are satisfied, then how do we find the value of fx?
So none of the constraint.
Not like x1 x2 is greater than 0 and lambda is less than 0, or lambda is also greater than 0. All these conditions are not satisfied. Then how do we go about the answer, minimizing or maximizing?
Can you show me the problem? Just
No, I'm just asking a general question.
Solve
Sir,
the
I think that was not
Rohini,
the
solve the problem graphically.
This one problem, you are saying this problem.
Just show me the
No,
problem. I'm not able
no,
to.
You can solve.
I'm not.
Now I'm leaving this. I'm leaving to you that what is the lambda value you'll get. I'm leaving for you.
I want
Means
to.
here is just.
No, I want to see the function which we are trying to minimize. X square plus 2xy plus what?
Yeah.
What is that function?
X square plus 2xy plus y.
Okay, that's what we want to minimize subject to x less than y square, right?
Maximize, you say.
Thank you.
No, I'm saying maximizing or minimizing. Okay, I'm not saying whatever the constraint you are getting. Okay, so either you are getting 2 points, 1 point. You have to think that that point is you are getting the maximum value or minimum value. Whatever the critical point, whatever the value you are getting, whatever the points you are getting. It's depend on there. Okay, so means I am saying, see, why I am doing this also that you will also know whatever the tricks, whatever the way you have, like so somebody says just add them and actually we reaches to some lambda. Somebody is do something else. Maybe sometime this equation is very simple, you can easily get. Sometime it may be complicated. So it's depend on the question, but in exam perspective, it is not going to be anyhow. You are not going to be stuck. If you follow the procedure, you will surely reach to the answer. Because that is computer CBT. You have to put the answer. This is a subjective one. I am leaving you, but there you have to put the answer. No, so how it will be.
Okay, sir.
To a standard method.
So can we go on to the topic of convex and concave functions?
Yes. So that is what here. That is so many things we have discussed here. The KKT also we have discussed and reaches to the one answer, -1/2 and 1/2, and we started with the Lagrangian only, and we reaches to this equation. We can solve. I can solve by this Desmos. I can reach to the answer, but let's leave this because here just need to find the lambda value and finally substitute, find the x value and y value, whatever the value you are getting. Just find that. That is your point. Okay, so now we have this. Either I can give another question, but let's do the convex and convex function and convex set. So convex set is a set is convex. We know convex set. A set is said to be convex set. Okay, if you have this property. In mathematically, we'll say S is a convex if you are choosing 2 points from that set. Okay, and if you are choosing this point, then this should satisfy. Okay, lambda time x plus 1 minus lambda y. Whatever the element we'll get here, this should be within the set. Lambda have some constant 0 to 1. This is what. And this is true for any. So this is for all xy. Any 2 point I will choose, and if this is this linear combination I am taking, if this linear combination is within the set, then we'll call it convex set. This is the only definition of convex set, I think. Yeah, this is the only definition. And once we have a convex, so main thing is there. So there are some property on the convex set. If you add the 2 convex set, then it will be a convex set. And there is one another thing is convex hull. Last time I was there, I was talking about the convex hull.
Sir, what is convex combination?
There is one convex combination. There is a thing convex combination. So convex combination is let's say suppose I have some fixed points. Let's say I'm taking points are 1, 2 in R2. I'm saying 1, 2, 3, 4, 6, 5. Let's say I'm taking this fixed points. Okay. Now this kind of representation, lambda 1, 1, 2 plus lambda 2, 3, 4 plus lambda 3, okay, 6, 5. Okay. By this way, this will be a point because as lambda 1, lambda 2 are real numbers. So this will be a point. Okay. So I am taking what is a linear convex combination means if I am taking this kind of combination, this is a kind of combination where this lambda have some condition, this will be added to 1. Okay. Okay. And the next is lambda 1, lambda 2, lambda 3 all should be from 0 to 1. So this kind of combination of these numbers, sorry, these points are actually called convex combination.
Okay, sir.
This is one example. This could be now have many points. You can extend this all any till any. So you can add finite many numbers, not infinite, finite many numbers. Sorry, finite many points, elements, finitely many elements, points. So this kind of combination is called convex combination. Okay, and by this way, okay, so let's say I'm giving 0.5 as a lambda 1 and lambda 2 is 0.3 and lambda 3 is 0.2. So by this way, if you substitute, we'll get a point. So this is whatever the point you are getting, this is a convex combination, means by these points I'm getting a point. Yeah, these all are actually, if you sum them, this is 1 and all are actually between 0 to 1. So this kind of combination is called convex combination. So same way, if I will start changing lambda 1, lambda 2, lambda values within this constraint, okay, within this constraint, any one by one, this is one set I got, sorry, by this lambda values, I get 1 point. Okay, similarly, I will change the lambda values another point. Okay, I will generate so many points. By this way, I will collect this set. Okay, all points are actually infinitely many points I can generate. All actually with I all actually contained within this set. This is called convex hull. Right? This is a definition of convex hull. You have given some finite numbers, sorry, finite points. Using convex combination, you are generating a set which is a convex set. So this set is actually convex set, and this is called the convex hull. So sorry. Convex so just convex hull is the yet.
So I think the function you explained for convex combination, that was convex hull.
That is a convex. Just a second, I just missed that. What is here actually? Yeah, I'm actually, yeah, I just missed that. That is yeah, correct. This combination is called convex combination, and by this way, whatever the generating set I'm getting, that is called convex. Yeah, I am correct. Sorry, I thought maybe I'm telling wrong, but it is. So this set is called convex hull, and this combination is called convex combination. That is what I said.
Sir, could you please explain convex hull again?
So suppose I have these 3 points. Okay, these 3 points I have, and this is the equation I am forming. Okay, this is one, not equation. So this is one combination I am forming. Okay, and now within this constraint, okay, within this constraint, using this constraint, okay, means I chooses lambda value one, lambda one is this one, lambda value is this one, lambda value is 3. Okay, I substituted here. Okay, I will get 1 point, right? This is 1 point I got. Okay, let's say I am now choosing another. Lambda 1 is 0.2, lambda 3 is 0.8, sorry, 0.7, and sorry, lambda 2, and lambda 3 is 0.1. Okay, again I substituted here. I will get another point, right? Similarly, one by one, similarly, I will change lambda values. Okay, lambda 1, lambda 2 values. I will change. I will get the set of points. So here I will get another point. Similarly, I will change that. I will get another point. Okay. Similarly, I'm changing lambda values and I'm getting the points. Okay. I'm just, so once I got these all points, I'm just collecting these all points. Okay. I'm just collected all these points in one set. This set is called convex. This set is called convex hull.
Okay, sir.
Means convex hull is nothing but the collection of all convex combination of these points. That is the definition. Convex hull is the collection of all convex combination, which is this one, of these points. So this is what happening now. I'm collecting all convex combination in this set. That is what I'm saying convex hull.
Can we calculate it also, the set of points?
Yeah, we can calculate.
Also?
So, but it have infinitely many.
Okay.
We can calculate as
Whether question can we frame like that also to find the convex hull of this.
So maybe question would be which one is belongs to the convex hull from the, maybe some point is given. Okay, some point is given. Let's say I'm saying
question. Some
8,
question.
5.
You take some questions of that.
So question would be, let's say I'm creating question here itself. Is the point, okay, is the point 8, 5, okay, belongs to the convex hull, where I'm saying this is the convex hull. Yes, at this set I'm saying yes, convex hull has, yes, which is generated by these 3 points. Is 8, 5 belong to that?
Just we have to check it, right?
Yeah, you have to check it.
We have to multiply lambda 1, lambda 2, lambda 3 to the point.
Let's checking that, just verify that is this belongs or not.
How do we do it, sir?
So yeah, this is good question. So
can you repeat the question, sir?
Sorry?
What is the part of a count?
So what is the question? Can you repeat, sir?
Question is this one. Is the point 8, 5 belongs to the convex hull? Yes.
No combination will give you 8, 5.
No combination?
No.
Okay, is it?
So what is S? Where S is given?
S is convex hull generated by these 3 points.
Yeah, but the maximum X is 6. And what you need is 8. You won't get even the X coordinate. Forget the Y coordinate checking.
No, you are saying like this, but there could be lambda value could be anything, no? So lambda is can be manage that. Lambda value can manage that.
No. Lambda has to be positive.
The lambda has to be within 0 and 1, right?
Best case I can take is lambda 3 to be 1 and lambda 2 and lambda 1.
Yeah, that is what. Yeah, so that is what you have to give some argument. Yeah, you have to do mathematically. So how we'll do this?
try lambda 1 plus lambda 2, 3 times lambda.
Yeah, that is what lambda 1. Okay, so use this equation. Sorry, use this one.
Yeah.
So I'm saying, is this point belong to that convex hull or not? That means this combination equal to 8, 5, right?
Yeah, it should.
This is what the meaning.
That's okay. Try it out. Lambda 1 plus 3 lambda 3.
So lambda 1 plus 3 lambda 2 plus 6 lambda 3 is equal to 8, right?
You will never get
and 2 lambda 1 plus
first equation itself will never match, because the moment you reduce 6 by 0.1, you are reducing 0.6 and then adding something which is inferior, so it will never reach 8.
I don't know. So that is what here. So you can okay. So let me one thing. So let me do this. So this is 2 lambda 1 plus 4 lambda 2 plus 5 lambda 3 is equal to 5. So now you know this is what? What is this? This is your system of linear equation. System of linear equation. But here you have 3 variables, 2 equations. If this system have solution.
Wait, 2 more constraints. Lambda 1, lambda 2, lambda 3.
How that we will check. That we will check.
And
the constraints are there. Yeah, this is another thing is lambda 1 plus lambda 2 plus lambda 3 is equal to 1. Okay, we can use this even. No, we have to set it to satisfy. So we have now 3 equations and 3 variables.
Correct. You will land up getting the lambda 1, lambda 2 being negative.
Okay, so if I will solve, then I am getting lambda 1, lambda 2, and lambda 3 all are negative.
No.
If anyone is negative, then in this case there is no.
It doesn't form a convex hull.
So I am telling the procedure actually. So we have to solve this system, and if this system has solution, once you got the solution, okay, you have to check is this all positive. Whatever the solution you got, all are actually belong to between 0 to 1. If it is satisfying, then we can say 8, 5 is actually belongs to the convex hull. If not, then no. Your answer is no. That is what. This is the procedure only. All are very silent. Is this true? Is this fine?
That's
Sir,
correct.
last part I did not get it.
You guys are still getting carried away by the symbols. I am simply applying common logic.
Okay, so what is your what you are using?
Yeah, listen to what my argument is. First statement, lambda 1 plus 3 lambda 2 plus 6 lambda 3 is equal to 8.
Yes.
Now assume that lambda 1 lambda 2 as the minimum, that is 0.
Okay, that is 0. Okay.
The lambda 3 becomes 8 by 6, which is greater than 1.
Okay, so you are saying lambda 1 and lambda 2 is 0. Then lambda 3 is going to be 1 in that case.
Yeah.
And this is going to be
more than 1. It will
okay, so if lambda 3 is 8 by 6.
Not allowed, right? So now
not allowed.
I take a small value from lambda 3, say 0.1. So I make it lambda 3 as a 0.9 and then put the value in lambda 2 so that I get my sum of the lambdas equal to 1. Okay.
No, so you are saying this is going to be, but no. So so I think this argument is not too generalized, because this is your assumption.
No.
But
I am taking it deliberately so that I can maximum. Look, the left hand side I got to wind up something coming close to 8. My target is 8. What lambda should I choose so that I can come to 8? Lambda 3, I should give the highest weightage.
Yeah.
If I give it 1, still I'm short of 2 numbers. So if I reduce that weightage, I will give it to the rest of the fellow who's are inferior anyway. So I will never reach 8.
Okay.
That's
okay.
Look, before getting into all the formula, we should also look at that. Is it feasible? It's beyond the region, so we can do half an hour calculation and then come back and then say, oh, it doesn't belong.
Yeah, right.
So when you start looking at the numbers and then apply in real life, yeah, can I get it? No, I won't get it.
Right.
If you've chosen something possible, then there is a feasibility. Yes, if the 8 has become, if the 8 was given as a 3, then yes, there is a lambda pass combination. Then second one I got to check.
Yes. I don't think mock is going to be considered accredited. No, I don't think. So
Yes,
yeah,
it's
right.
same
So
for
before
second
doing
purpose.
Another question. The mock answers are wrong.
mock, some questions
The
are wrong.
answers which is given, they are wrong.
Some questions are, I think, typo mistakes are there.
The answer is not typo. Even the answer given is, instead of answer being right, it is showing wrong.
Two questions perhaps.
Question number 4 or 5 or something like that. So the answer is, I don't know. It is going to the 4th place of decimal. And I don't know, it's not mentioned there also in the question and the answer what they are giving. It all varies between whatever value of sine or cos you take, they cannot be up to so much places of decimal. Answer is wrong.
Yeah, it may be.
Just an input, it's not very important.
It may be. Okay, so here somebody says I missed that last part. So here last part is you have system of linear equation. Okay, you solved it. Okay, and you find some values. Okay, some values you got. Okay, some values here you got, here you got. Here. Just check that all are actually between 0 to 1. If anyone is missing, then your answer is then your answer is no, means this point not belongs to the convex cell. If all are actually satisfied, then you are correct. Yeah, this point is actually belong to the convex cell.
Okay, sir.
Okay, that is the last one. Not possible. Okay. Minus is, yeah, 1 lambda 2 you got here. So yeah, all of you can able to see here the chat one. This could be easily solved. Well, not easily solved means if you solve it, you can reach to it. So lambda 2 is negative here. Yeah, link of the session is already updated in the calendar. Here you can see it. Okay. Calendar I have updated here. This is here.
For what? Link for what?
Link of the YouTube is asking. So see here the lambda 2 is negative, lambda 3 is 2 is there, which is never be possible. Means this system don't have, means it have solution, but whatever we have the constraint, it is not follow that. It is not following that. So means this point is not belong to the convex. So this is one question of can think from the convex cell part. This kind of question you can think. So I hope all of you get clear with this convex thing and convex hull. Okay. So sometime, see, I solve this by the definition only. Sorry.
Some confusion is there always in this convex type of thing. Well, we solve it, sometimes it is not straightforward.
Yes. So see, one thing is there, whenever you are stucking or so whenever you are not able to solve, just follow up the definition. So here somebody is asked that what are the steps we will do, or what are the steps we will follow. So use the definition as the definition is there. Use this definition, and we end up with this equation.
Approach with the definition only.
Next is a convex function. So convex, this kind of convex function is said to be a function is said to be convex. The basic definition is which is a very much useful also epigraph. EP graph of the function. IP graph. What is the EP graph of the function? Is that if I'm supposed the graph of the function is this one, okay, then this portion.
Epigraph means it divides the whole space in two parts. Is it?
No, here what is the definition? That is what I'm saying. I'm not sure about that. What you're saying. Epigraph is this one. This epigraph is a set which contain actually this all.
Now, how can we say in the language without graph? What is epigraph?
So without language is this one. Then whatever the function is defined. Let's suppose I'm taking for function f. So the set where fx is greater than here is y value are greater than this. This is what it is. Sorry. Yeah.
Let's set up the points which are,
or this is the condition x and y such that y is greater than
fx. Yeah.
Or meaning of that graphically is this one. I am collecting all those points, which is this one. So if so, not only this one. This set should be convex.
If the epigraph is a convex set, then it is a convex.
Yeah.
Right.
If this set is convex, this epigraph is a convex set, then this function, this f, this function is actually convex function.
Convex function. We have to plot the function first so that we can decide, right? The only way is that.
If suppose the graph of function is this one, is this function is convex?
No.
Not right.
No,
the simple
sir.
reason is if you think about the epigraph case, okay, then if you take point here and take point here, this set is not convex. The epigraph is not convex. And simply it's look like also, see the convex meaning is, if you use the 12th standard, then convex function are kind of this one.
Yeah.
So this is not following that.
My question is
this way
that can we decide on the basis of analytical only without plotting the graph? Do we have some method?
So yeah, so for that case,
we do not want to plot the graph.
Yeah, if you don't want to plot the graph, then the definition is you have to follow this one. Lambda time x plus 1 minus lambda time y. This should be lambda time fx.
Less than lambda time fx.
This is what the definition, right?
Okay. Yes.
Just one minute, let me check.
But when we do this in the function itself, then it becomes very difficult to decide whether LH is less than or that or not. How at that case we can suppose some function is there. Can we take an example for this only? Some not simpler example, some complex function like.
So this is the definition here. Example is
because in the lecture also example was not there. Questions were there.
So let me tell you, let fx is equal to even this.
Now take the example of x and y both. Because
so I have this function. Okay, I have this function. I want to check is this convex or not. So you have xy means it will come in automatically x and y there.
Okay.
So if you want to check it, so here suppose this is the what we have. So f of lambda time x plus 1 minus lambda time y. Okay. This means that this means that f of. Okay. So if you want to check it, so take the left hand first.
Yeah.
Take the left hand and here the right hand side. Okay, and left hand side should less than or equal to right hand side. That is what we want to check it.
Yeah, we want to
This
check
is
it.
the way to check. So here this is equal to f of lambda. So if you have this one, so this is going to be lambda x
Lambda
plus
x
1 minus
plus
lambda.
1 minus lambda y, the whole square, plus 1.
This is what it is. So this is going to be lambda square x square plus 1 x y plus 1. This is the left hand side. Right hand side is, if you take the right hand side, this is lambda, and right hand side is x square plus 1. Okay, and plus 1 minus lambda, and y is going to be y square plus 1. This is what we have, right? This is the right hand side.
Lambda x square.
Correct? Plus 1 minus lambda.
RHS lambda into
Y square plus.
Yeah.
Plus 1. So here lambda x square. So here is lambda x square plus lambda plus here 1 minus lambda y square plus 1 minus lambda. So lambda will be cancelled out. So finally we have lambda x square plus 1 minus lambda y square plus 1. This is what we have.
Yeah.
And here we have this one. So lambda x square, lambda 1 minus lambda x, lambda square x square, 1 minus lambda square y square, and this portion, and plus 1 is there. So is this less than or equal to this one?
How to decide here?
So this will be decided each term. So this one is there. So that means this is nothing but I should to compare this to lambda square x square plus 1 minus lambda square.
It is not less than. It is not less than. We are just checking it whether it is less than.
So means here both sides 1 is there, means this will be cancelled out. This will be cancelled out. So finally I need to check this portion only. These two. Let me, why I'm doing this. So it means this should be happen. So now what is here? This is lambda square here, and this is just lambda. Okay, and this is lambda 1 minus lambda square is there, and this is just 1 minus lambda. So which one is going to be? And we know lambda is between 0 to 1, and if you are squaring, this will be always be lesser also, right?
Yeah.
This will become lesser. Okay, this is what is first thing is happening. Okay, and now what about this case? This x and y is going to be this 2 lambda. These two, using these two terms are actually fine, but now this third term is
this was my question. When we reach to this point now, we get stuck to whether to decide, how to decide. Another way is also there to find it out.
So let's do, so the way is that let's do ahead. So this is going to be x square common. Okay, I'm sending this to this side. Okay. So means here what the way is that, the second way is that this is the one and this is the second one. Okay, if I'm subtracting of 1 and 2, and if it is less than 0, then true. If it is not, then fine. So let's think a function. Okay, let's think a function g of xy, which is of this one, lambda square x square plus 1 minus lambda square y square plus 2 1 minus lambda x and y minus time, sorry, minus y. This is what it is. Means I'm subtracting. So this is, you have a function g of xy of this case. Now I have to check that is this always less than or not. This is always negative or not. This is what is the checking. So if you take here the x square common, we have lambda square minus 1. Sorry. Lambda square minus lambda plus y square. If you take common, this is 1 minus lambda square minus 1 minus lambda plus 2 of 1 minus lambda. Lambda is I missed it here. X and y. So something is there now. So what we can say about this? This is going to be less than or equal to 0 or not? Always.
Very difficult to decide.
So this portion is negative. It is very clear. This portion is negative. This portion is also negative. What about negative, right?
Yeah, the whole thing negative.
This is negative. What about this portion? Will this be negative? How you are saying negative?
How the second one is negative? 1 is positive.
1 minus lambda negative.
Yeah, because these numbers are actually between 0 to 1. No, so if you are squaring, then this number is lesser than in comparison of this one.
Okay. After squaring, it will be lesser. Negative.
What about this term? This term is a big problem. What you can say? This is going to be negative or positive?
If lambda is, let us do inside lambda minus lambda square. Put lambda inside lambda. Lambda minus
Negative
lambda
if
square.
lambda is more than.
If lambda, no, it is positive, sir.
It is going to be positive. Then how much it is positive? If these two are negative and adding them, so these two are negative. How much this is? Means this is actually our function is convex, right?
Just small positive.
Our
like
function is
lambda
convex,
minus lambda square.
This function is going to be this one, right? Our function is convex, we know by graph.
Yeah. We know that it is a convex function, but we want to check it by analytically.
So this is negative, and I'm adding these two negative. So that means this is positive, but this is going to be lesser than these two once we are adding them. So a bit typical, here it is a bit typical. I'm now see this is that much I did here. So anyhow, now you have to think how I can now do it here within this time. So it will actually take time. So actually we are in session. So this is how we have to do.
Actually, this was my question, because at that time we will, in the examination, it will be very difficult. So we have to pass it on there. After doing all these things, we have to pass it.
Yes,
because you are not able
but
to
this
decide.
is what it is. This is how you will follow. Like this is how the analytically.
Yeah, approach is this. I know in the examination. Certainly, we should solve it. Certainly, no. Some way should be there to solve it. But we are not getting here the approach to solve it certainly. If you are approaching rightly, then it is not certain that you are going to get the answer. This is the problem. Okay, let us proceed. This is the way, because we don't have
this
any.
Is the way actually.
Okay, fine.
So there are some property of the so these are the convex properties. So there are so many properties, small properties.
We have to apply one by one then.
Either there is a, if you are thinking the composition, we have two function F and G, and we are thinking F compose G. Okay, so either this one is convex. Okay, this one is convex plus non-decreasing.
Non-decreasing.
This is convex. Then this composition is convex, and the second thing is this is. The another is if this is a linear, and the second one is convex. Okay, convex and linear, I think, or you can check, or just a linear. And this is convex. In this case, the composition is convex. You can just check it. That I think this is just for linear.
Convex and non-decreasing is compulsory. And G can be convex or non-convex.
And the second one you can check some condition is there. Okay, this is just simple.
Yeah, it is okay. This is okay.
There are some composition property, And if our there is one thing is that our function is multivariable. Our function is multivariable, then what we will do, we'll find the Hessian. Hessian, all of you know what is a Hessian. Hessian matrix is double derivative.
Hessian matrix will decide properly.
If the eigenvalues are no, so sorry, this matrix is positive semi-definite, then this function is convex.
Yeah.
Positive semi-definiteness is there. And one thing I want to add from my side is this PDF one, that if our function is twicely differentiable, no, so all of you can see it here. If a function is there where it is a twicely differentiable, okay, this is for one variable case, okay, this is for one variable. I'm saying if it is twicely differentiable and double derivative is greater than 0, then your function is convex. You can
Pardon, once again.
This is the, okay, let me take the screenshot of it.
Okay. Share it.
I'm just taking this screenshot. If our function is one variable, okay, please see it. Our function is one variable. This X is subset of R. Our function is from R to R, okay, or subset of R. It is twicely differentiable, means 2 times we are able to get derivative, okay, like for the function is fx is equal to x square, or maybe x to the power 5 or 4. Means a kind of polynomial, a kind of a function which is twicely differentiable. We need a second derivative, okay. So if it is twicely differentiable and the double derivative is always greater than 0, okay, within the domain, then your function is convex. If suppose I am giving function fx is equal to what, x square plus 2x plus 1, or let's say x cube even plus 2x plus 1. Okay, if you derivate it, we don't know what is this convex or not. If you derivate it, this is 3x square plus 2. Okay, I'm double derivated. This is 6x plus 6x only. Okay, so is this 6x is always greater than 0 for whole R? Is this? Will this be? No. If you take negative R, negative x, then it will be negative. So this is not. So this function is not convex. So you can use this property.
It means x and y, suppose some variable comes after the double derivative, it means it is not greater than 0 equal to 0, right?
Yeah.
And in that case, it is not convex. If it is a constant, then it is a convex, right?
If it is our function is this one.
Yeah.
Okay. So let's derivate it. This is going to be 2x plus 2 and double derivative is 2.
This is?
Which is always greater than 0 for any.
Yeah.
So this is a convex. And even you can check it. This is a quadratic. Okay. This is a parabola.
Yeah.
Some shifted parabola. So we can use this. This is an important one for the one variable case.
Where did you share this proposition notes, sir? Screenshot? You shared it?
No, I just taken from internet. I thought maybe it is important.
Okay.
So this is actually true. If you want to check concave is just negative, means what is that? Minus f of x should be what? Concave is one. When we'll say concave? Concave is if minus f of x is convex.
Yeah, then it is a concave.
So if you apply here, what is that? Double derivative, so less than or equal to 0 for all x. That is what for concave. This is what happening, right? Because negative, if you do double derivative negative will be there always.
Yeah, if it is not convex, then it is always convex. right? No.
Sorry?
If it is not concave, then it is convex.
No,
If
not
it is not convex, then it is concave, right?
No, not necessary. Not necessary.
Okay.
This function is not convex, right? This is
A
not
function,
convex.
a function can be neither convex nor concave, is it?
This one.
Okay.
Think about this function.
Okay,
Not
very
concave,
good.
not convex.
Okay, fine, right.
Yeah, sir, can we just cover the other topics as well, sir? We are running out of time. So just from the exam standpoint.
Yeah. So actually, so we are almost done KKT. KKT is, I'm not going to deal so much because one problem we solve on the KKT.
Correct, yeah. So, sir, just if they ask anything related to KKT, right, can we just solve it using the LLP, like the graphical method?
Yeah, if it is in two, so yeah, so let me LLP method, sorry, LPP.
Yeah.
So if it is in two variable, no, suppose I am done with the convex and all. Okay, now I'm just going to be the KKT and a small. I want to discuss on a small KKT. So I want to now I'm. Please make note. Okay, note is that. Okay, if in exam your question is a very complicated or on the definition is given. Okay, on the definition, the problem is given on the definition. So my request is follow the KKT steps. Okay. What I mean to say, find the stationary condition. Okay. Find the complementary slackness. Find the primal feasibility. Find the dual feasibility, and using this all, try to solve. Okay. Within the solution, you will get some key point where maybe you will get some options which matching to that, which will match to that, and you will choose the correct option.
Okay,
Maybe
sir.
question
So
on
in
ask
these
bit
points,
like
it will
this.
be just to find the X star or the lambda star, right?
Yes. So I mean to say, try to solve the problem. Okay. So it may be a complicated question, but it is within the solution. If you start solving, the option would be asked from the steps. Okay.
Yeah.
While solving, you are solving, maybe you reaches some steps. The option may be asked one is from this particular step.
Understood, sir.
So how you will choose that? If you start solving one by one, then you will choose correct option. So my request is follow and try to solve step by step KKT condition to maybe if the question asked within the steps, you can choose the correct option on that.
Yeah.
And this is one note, and another note is suppose your KKT is given within two variable. Okay, so suppose I have some minimizing problem. Okay, some objective function is given where some KKT constraints are given. Let's say two constraint is given. So if you are facing difficulty with the KKT, okay, then use the graphical method. You can draw the graph of the constraint. Okay, find the feasible region. Suppose this is x plus 2y less than or equal to 1. X is less than or equal to y. So graph of this feasible region is this is your G2, and for G1 maybe this one. You can check it. I think this is only. So feasible region is this is what the feasible region. So maybe your region may not be bound. In that case, you will not get the minimum. So maybe the region here is the minimum you can get. If it problem is generally for minimizing. So find the means you found the region, okay, where suppose a kind of this region is given. So feasible region is this one. So or use the corner point, whatever the points you will get here. At the corners, you will get the optimum solution.
Just a doubt here, sir. So if the optimization function is like to minimize, so the conditions should be less than or equal to, right?
Less than or equal.
And if it is maximized, so we need to like multiply by -1 to make it like greater than or equal to.
Also, as in it is not in lecture, so you always think that this is the condition with less than or equal to and minimizing.
Got it, yeah.
Because not so taught in detail if it is minimizing, maximize, maximizing problem is given or conditions are constraint are given greater or equal to. If you see in the lecture, it's already mentioned that some objective function minimizing and constraint is always less than or equal.
Yeah. Yes, sir. Got it. Yeah.
So this is one. This is the. That is why this week 10 is a very small portion of the optimization.
Just one question here. Just you drawn a triangle as the solution. Okay, the triangular region where the three intersection happens. The optimum region may not be on these three edges. No?
So the optimum is not going to be here on this here. It is always going to be at the corners.
So that's what I'm saying. It may not be on the corners also. No? It can be on the edges. It can be on the side also. This three, if you take a triangle, it can be on.
No, it is going to be on the corners only.
No, there are questions in which the solution is not on the edges, not on the intersection, and it can be on any of the sides.
Any of the sides.
Yes, any of the sides. The optimum solution may not be the point ABC, but it can be any point, say D, which is the intersection, which is in between A and B.
At the tangent.
So
yes, typically tangent or whatever. Especially if you take the circular contours.
Yeah, if it is not if the constant is not a straight line, then in that case a tangent point becomes the solution of
that. Not only that tangent, you have to understand which is that tangent. It should be tangent to the line L1 or L2 or L3, depending on the conditions they will be.
In that case,
it may not be necessarily on the edges.
Yeah,
it can be on
not.
any of the sides as well.
Any of the sides also.
Depending on the objective function, what you are looking at to minimize or maximize.
Okay. So actually the best thing is what, if you have the minimizing problem. No, so if the problem is like this, okay, suppose the problem is this and the problem is for minimizing. So if you substitute here so on the edges you'll get infinitely many things there. Then it will be problem. The corner is actually give the finite fixed one.
No, sir. Suppose the constraint is a curve.
Okay.
Then at that point, at a tangent point, we get that. In some cases.
We are saying the objective function is say circle. X square plus y square is equal to say you are minimizing or maximizing x square plus y square.
Okay.
So in that case, it may not be on the three intersection points.
In the three intersection points. Okay.
In such cases, we normally get when we plot it, we see that.
Okay, but don't go beyond of it. Actually, so it is all or not in the lectures. How we can say this?
Yeah, in the lectures it is not there.
No, it is not there, but it is asked in the question.
Yeah, in the
what do you call
questions
that mock question? It is there. If you go by this method, you will not get the solution. If you go by the intersection, you have to solve by that tangency, and you will get the optimum point is lying on any of these line in L1, L2, or L3. There it is optimum. It is the least. Because that's the question. Typically blindly you cannot take these three intersection points. That's depends on the objective function, the nature of the objective function.
Nature of the objective.
Yes, it's all basically depending on the nature. So if you have a linear, you can go with this particular approach. But if the objective function is a bit different, then you have to think through.
Where the objective function may be asked like the quadratic form also, or it will be only the linear type of thing?
No, it could be quadratic, it could be anything. Objective function
in that case.
So because if you say if suppose we are not solving by this method, if you are solving by the KKT, so the KKT doesn't matter your function, how the function it is. It will just follow the rules. It will just follow the rules. If you are able to reach the answer, then you have to give that. So objective function could be anything.
That's why Srikant, if you look at the mock problem, the solution region is a trapezium. Okay, not trapezium, it is a quadrilateral. So that quadrilateral, if you take the 4 edges, you'll not get the solution, optimum solution. It's a
In the mock,
quadrilateral with 4 points.
in the
But
mock,
that region, the edges, 4 edges, will not give you the optimum solution. That's my question.
a number of questions, the 2 or 3 questions in the mock also very confusing type of answer is not, I think, matching also where we are there.
Okay, let me see it.
Okay.
Which one is there? Which question you are saying?
I'm saying go to that, graphically, if you look at the question number, I think that question, that is the question, which is looking for the optimum.
This one, I think.
Not this one. These are mock, this is?
Yeah, this is a mock.
Okay. Then where is this?
Yes.
Which was released 2 days back, some mock was given.
Yeah. So, question number 4, I think.
Question number 4, na? Question number 4, actually.
So this PDF is a older one.
No, not this.
1 minute.
But this is not the mock, na? This is different.
Then, yeah, it is. Yeah, it is a different.
It's a different.
It is. This one is different.
Anyway, let's forget that. You can continue.
Okay.
Yeah, I think that's the one. Go down. Let's go down. I think let's go down. It will go down, I'm saying. Or up, go up, sorry, go up. Yeah, this is the question.
This is the problem.
Yeah, this.
Minimizing function where the sign is okay. This one is there. Yeah, so here it is converted the standard one. Okay, standard form. Okay. Yeah, this is here it is mentioned. Okay, so it is converted in the less than or equal to. Now the KKT condition will follow. Minimizing this. Okay. Complementary slackness is this one. Primal feasibility is this one. Dual feasibility is this one. Now case 1. From 3, let u1 is equal to 0. So 3 we have this one. u1 is equal to 0. So if u1 is equal to 0, then this will we have, and from here x1, x2 value will get. Substitute 7 and add in 4. Okay. So you are solving this by which way?
I have solved it with graphical method, so.
Okay, if you
that
are
is much faster. That will be faster than this.
If you solve this by graphical, so here this is going to be.
You can find out that region which is where the solution.
2x1 plus 3x2. Okay, just a second.
What we call the standard form or standard expression for the KKT condition, always less than equal to 0.
1 minute, I will open it. 2x plus 3y greater or equal to 6. This is the reason. And the second one is 12 minus 3x minus 2y. 12 minus 3x. 12 minus 3x. Okay, sorry. 12 minus 3x plus 2 greater or equal to 0. Plus 2 or minus 2y minus 2y. Minus 2y. So this is the reason. And the next is both are positive. That are 2, 3, 7. So this is where it is. Where it is most. So this is the reason we have. So intersection greater or equal to is this one only. So this reason is not bounded. So graphically, then we cannot solve this. Okay. The first thing is that this is, see, this region is not bounded. You are saying we will get a sorry, you are saying some region we will get, right?
Actually, in the case 1, where we solve it analytically, then it becomes lambda 1 is invalid. In that case, then we go to the case 2.
If you solve graphically, so graphically this we cannot solve because the region is not bounded. So here, this,
yeah,
graphically it will be problem.
But I have solved it graphically. Should I tell the approach?
So how will, the region is not bounded, then how you are solving it?
Because you could see the objective function is basically concentric circles. So it is x minus 4 whole square plus y minus 4 whole square, which is basically series of circles. So it will, the least point where it is touching that that's a straight line, which is 3x plus 2y greater than 12. So that's the point. If you take a point, say alpha beta, and if you take the slope of that with the center of the circle, the point.
So actually, indirectly you are doing this. Indirectly you are doing KKT only.
Yeah, indirectly I'm doing KKT, but I'm doing KKT only.
That is what the KKT.
Yes, I'm doing KKT only, but by graphical way, the solution will be much faster because I don't have to look for alternates and all that, checking lambdas and checking the values of u and all that. So I can straight away know these are series of concentric circles. So let me take the tangent point. It will be the distance. It will be having a slope perpendicular to the other line. Its slope will be minus 1 by m, and that lying on that line, it will give you the point alpha beta, and that's the point where the value is given. Thereby, I got the solution.
Okay. Okay, so yeah, you are saying graphically, but what I was saying for graphically is that if your region is bounded, okay, if your region is bounded,
I understand it is not bounded, but the approach which you have taken was I will be on the surface where it will be least from the center of the concentric circles.
So what I mean here, so okay, I got your point. So what I'm here is that if your region is bounded, okay, if your region is bounded, in that case, the answer is going to be on the corners.
Right. That is it. That is it.
And for this case, our region is not bounded here, so we cannot do by this method.
Any other topics to be covered, sir, for week 9 and 10?
So that's all. That week 9 and 10 we have already done. I was just discussing
Okay,
this
so
one.
this is
I'm now going
important
to
from
the
the exam point of view, right? Okay, sir.
So I just a small thing I was telling that if region is bounded, the answer is going to be on the corners. If region is not bounded as this case, then I'm not. So we are not going to deal with this our method, and we'll only follow the KKT.
KKT method.
As
Okay.
this one.
Now we can just share this PDF, sir. This one.
This PDF.
Yeah. Sure. Thank you.
Okay, and that's all from my side. Thanks everyone. Thanks for joining.
Sir.
Yes. Yes, sir. Yes, Ranjit.
Okay.
Sorry, somebody is saying something.
Yes, sir. Sir, will there be a session where we are going over the mock?
Okay. Yeah. So tomorrow is going to be the session. So I will tell to Mayur sir to dealing with the mock also.
Okay, sir. Thank you.
Okay. Okay. Thanks,
Sir,
Priya. Yeah. Yes.
Sir,
Yes.
what was the level of paper?
Level of paper is it will be moderate kind of what I will say moderate or even how I can decide. So but the thing is that whatever we discussed today, try to be sure that this one important thing, while solving KKT, you remember that you follow the steps, and while solving you will choose the options. So this is one case, and this is one important. If your double derivative is less than or equals greater or equal to 0, if you have a function of one variable and twisely differentiable, this is a very, very fast trick to So these two are actually important from my side for the interim. Okay, these two are actually enough for week to deal with week 9 and 10.
Okay, sir.
Okay, sir.
So can you please pin the PDF? I mean, I just joined it.
This one. This. Okay. Let me pin it here. Then I can easily get it. Are you able to get it now?
Yeah, sir, we got that. Yeah.
Okay.
Yes, sir. Yeah. Thank you.
Okay. Thanks, everyone.
Okay, sir. Good night.
I think tomorrow is I think next revision session. I think so. Yes.
Yes, sir.
Yes, sir.
Week 11, 12.
11, 12.
Okay. You will take the session, sir?
No, Mayur sir will going to be.
Okay. Sir.
Okay.
Thanks for your time, sir.
Thank you. Thank you, sir.
Thanks.
Sir, one request, sir. Do we
Yes,
have
sir.
do you have some solutions on KKT 2 or 3 set of questions properly done so that we can follow the same thing? Because solutions are not where they are properly.
Sir, it's kind of like different in different cases, right? So if we have a standard process, maybe I think we can.
We will do that so that we can follow the same approach, because these are the confusing questions every time we get